My pleasure to invite Dr. Pierre-Emmanuel Emeriau, who is quantum information scientist at Quandela, to take the stage. Thank you.
I can use Cool. Okay, thanks a lot, everyone. Thanks. I want to thank the organizers also for this magnificent event. I'm really proud to be here in front of such a large crowd of quantum enthusiasts. So I'm Pierre-Emmanuel. I'm leading the quantum algorithm team at Quandela. And I guess maybe I'll present a bit Quandela because I guess it's not that known in the US. So Quandela, we are doing a photonic quantum computer. It's a full stack strategy. We are about 80 persons now, and as I mentioned, like we are doing full stack, so we have profiles ranging from semiconductor physics, optics, up to you need a cloud access, so developers and also quantum information scientists, and we are based in Paris region. And so, what's the technology behind all this? So I mentioned it's photonic quantum computer. The technology are these semiconductor quantum dots that you see here. And so basically, we like to call them like French pastry, because you see it's like really neatly designed. So the idea is that you have an optical cavity with a quantum dot inside. And you should be able to get out of that a deterministic source of single photons. So you shine a laser on the quantum dot, then it relaxes by emitting a single photon, and the optical cavity should be designed so that it works at very high efficiency. And so Quandela started in 2017 as a hardware provider, so it wasn't full stack. And so the idea was just selling this source of single photons with all included. So you would have like cryogenic, single photon sources, all the electronic control, all the filtering, so all of the optical components afterwards, with a very high clock rate for emission of single photons, and like very like mild cryogenics. So you just need to go to the Kelvin temperature, not the millikelvin, so it's very low cryogenic, and so then it's kind of compact technology. And so we're still selling the source, like the device, and from that we get a lot of scientific publications from all over the world, because we have a lot of academic groups buying this state-of-the-art optical emission of single photons. And then, to be a bit more precise about the technology, so to me it's kind of best of both worlds, because you have this kind of matter-based qubits, the atoms, the quantum dots that you can think of as atoms, single atoms, and you can play with the spin of your quantum dots to act as a qubit. But also these quantum dots, they can emit single photons, and then you have a flying qubit that is, of course, that has a very long coherence time, because it's just like a photon in a transparent media. But then you have downside, like it's prone to losses. It's very hard to entangle single photons together. So like you have to play a bit with pros and cons. But we'll see later that it's very interesting to be able to have this matter and flying qubits in our technology, because we can use actually the spin of the quantum dots to produce linear cluster states, or I mean like states of like photonic states that are already deterministically entangled, which is very nice. And so then the journey continues. So in 2020, Quandela shifted a bit and decided to do full stack, hiring a bunch of theoreticians like me. And then 2 years after, we launched our first 6-qubit machine on the cloud. So it's cloud accessible. Everyone can use it. And we're actually publishing the Nature paper, the Nature Photonics paper quite soon on this, like in the coming weeks. And so basically, to get through the technology with you, it starts, as I said, with the quantum dot here, that you excite by a pulse laser that emits then a trail of single photon. So then you have an optical filtering, all of that, and you go into the demultiplexing that will the job is just to take a string of single photon and put them arriving at the same time on the chip, the optical chip. And then you can tune your interferometer, get your counts on your CPU, and you can, of course, connect to the cloud, to the CPU via cloud access. And this is done via Percival, which is our software suite for linear optics that you will use during the hackathon. So this is really like kind of a sketch of what a NISC device would look like. It's not what a fault-tolerant computer would look like. Then we need to go to a different solutions. And so, as I said, we are cloud access. I think it's very nice to have cloud access because people can actually use your machine, test it, and I mean, you can't lie on the numbers like they are what they are. Then we compute some fidelities that are, useful to benchmark the technology. We are, of course, improving every day, every month to try to reach higher fidelities. And also, in the paper I mentioned, we demonstrate for the first time generation of GHz state. So if you want to apply schemes like fusion-based quantum computation for fault tolerance, then you need to be able to have a resource state that you fuse together. So you need to produce reliably this resource state. And so this is state-of-the-art restore generation for GHz state. But of course, the idea is to go very high and to push the limits on the fidelity for those states. And so when you have this, computer and you're institutions like me, you start wondering, okay, but what can I do with it? So then we implemented a bunch of quantum machine learning algorithm on Acela, which is like kind of a hybrid computation where you have a CPU controlling your QPU, and you want a fast clock of acquisition so that you do a lot of runs of optimization and try to converge to your solution. So we implemented some classification tasks, some PDE solving, and also some rational Hegel solver to reach ground state of molecules, for instance. So like some applications we can do nowadays. It's not quantum advantage, of course, but it's still nice to kind of understand how it works, how you have to think the cloud so that it works for an external user, etc. It's very challenging. And also, you can reproduce paper very easily. So yeah, Valeria is in the audience. So it's a paper that she put out in 2021, a Nature paper on reinforcement learning. And in the tutorial just later, I'll show you how you can reproduce the result of the paper in like 30 minutes. And it was like a Nature paper from 2021, which is hard work. I'm not saying it's not hard work. It's just like, like the technology progress rapidly, and then now you have kind of automated device and like we can do quantum linear optical computation on the cloud now. It wasn't possible in 2021, so that's very nice. And then you have to think, of course, how you want to scale up. So we have kind of a short-term roadmap where the idea is just to scale the number of photons and modes in which you can play with. And because you have photons in Fock space, it's kind of a larger space than what you would have with qubit logical computation. We also have a progress on the GPU simulations to push the limits of what we can do on photonic devices. And also, of course, we're also thinking about error correction. And so for error correction, as I mentioned before, I guess the idea with our device would be to use the fact that you have a matter qubits that can emit chains of entangled photonic qubits, so linear cluster states, or if you have entangled quantum dots, you can do 2D cluster states. And from them, it's much easier to do schemes like, for instance, fusion-based quantum computation, or even do something a bit different, which we published recently, which is a spin optical quantum architecture, where the information is stored in the spin of your quantum dots, and the flying qubits are just performing the gates. And with that, I am going to thank again the organizer and conclude with my presentation.
Thank you, Pierre-Emmanuel, and thank you, Nate and Daiwei. We will have a very, very short break, like 5 minutes max, because we are very fresh. It's still the first day, and we will have a very exciting panel discussion. So I invite the speakers from the industry to come to get ready, and yeah, we will soon resume in 5. What? Ah, yeah, sorry. So at 2:20, be back here. Thank you.